uno.
Here we have all the electric fields for each case where you have a point charge, a finite line, an infinite line, ring, disk, infinite plane, and parallel plate capacitor. We're going to start with a point charge, and this is simple where you have one point charge with a charge of q that's a distance r away from your reference point. This equation is going to be a simple kq over r squared times your r hat depending on where your reference point is. Next we have the case of the finite line where you have a finite line of length L where your reference point sits on a perpendicular bisector to that line L. Your point is going to be a distance r away from that line, and you're going to find this equation by integrating a small sliver of charge, which is dq equals lambda dx, where your lambda is your charge density. And this equation, after deriving, comes out to be kq over r times root r squared plus L over 2 squared. Now your limits of integration here are going to be negative L over 2 to L over 2, and that will give you this equation once you integrate. Next we have the infinite line, and this is where you have a line of charge that's going to extend out in all directions, like this. Again, you're going to find a sliver of charge, which is dq equals lambda dx. That's a distance x away from the line, and this distance r is from your small slice to your reference point. This time your limits of integration are going to be 0 to infinity, and you're going to come out with the equation 2k lambda over r. Next we have the case of the ring, and this is where you have a ring of charges, either positive or negative, and the ring sits on the xy axis and is a distance z away from your reference point. This time you're going to take a slice that is going to be an arc length, so therefore your dq is going to be equal to lambda ds, where your s is equal to r theta. After deriving this equation comes out to be 2 pi r, which is your radius, which is this and not your distance from here to your reference point, times your k lambda z, and that distance z is from the middle of your ring here to your reference point. All of that is over r squared plus z squared to the 3/2. The next case we have a disk, which can be thought of as an infinite number of rings over top of each other. The only difference in this one is going to be your charge density is going to be sigma instead of lambda, and that's going to be coulombs per meter squared, because your area of your circle is pi r squared. This time the equation is going to be 2 pi k sigma times the quantity 1 minus 1 over root r squared plus z squared. The final case is where you have an infinite plane and you have a point h that is a reference point that is a height h above the plane. Now this plane extends in all directions because it is an infinite plane. In this case, h is not dependent. Your electric field is not dependent on h. And after deriving that, you get the equation E equals 2 pi k sigma, which is also equivalent to sigma over 2 epsilon. This 2 epsilon is your permittivity constant. And that is all 6 of the cases where you have point charge, infinite line, finite line, ring, disk, and infinite plane.